Hello, this is Spencer Lyon, and in this lecture, we will continue learning about graph theory and we'll build upon the concepts that we've previously studied. Before reviewing today's lecture, which is on weighted graphs, you should have already seen the introduction to graph theory, as well as the material on strong and weak ties or strong and weak edges in a graph. The goals or outcomes for this particular lecture are for each of us to know what a weighted graph is and how we might be able to construct them using Network X. We'll also learn about and practice implementing the shortest path algorithm that will allow us to find the minimum cost path through a weighted graph. The key references for this content uh, include sections 5.1 through 5.3 of the Easley and Kleinberg text, which you can access here at this link. So that we're prepared to run the code examples throughout the notebook, we'll import the necessary packages here. You see that we have our network X import under the alias NX, and we'll also read in our old favorites now, pandas, numpy, and matplotlib. Finally, we'll instruct matplotlib to make sure that the generated figures get displayed directly in line. So up until this point, we have considered a few different types of graph. We've talked about undirected graphs, and here the key feature are that the edges simply connect two nodes, say A and B, to one another. There was no notion of the strength of this edge or the direction. All that was noted in an undirected graph is whether or not two nodes are connected. We talked about an extension where we might consider that each edge has a direction. This is what was called a directed graph. And some examples of directed graphs might include things like a global supply chain, where the the firms that harvest raw materials may sell to firms that construct intermediate outputs. They, in turn, may sell to firms that construct final consumer outputs. In this scenario, you would have nodes for each firm. Let's go ahead and draw this. You would have nodes, say, for the raw materials firm. You'd have another node for the indirect outputs, the consumer outputs, and finally the consumers. And when the arrow or the edges may show us the direction that goods flow in this network, where the firm that is responsible for harvesting raw materials would sell to the firm constructing intermediate outputs, who sells to the firm constructing consumer outputs, who finally sells to the consumer. And so the direction here of the arrows is significant. It is uh, unlikely that the link could flow the opposite direction. Consider a consumer trying to sell to, say, the producer of a good. That's typically not how we think about these supply chains working. So, understanding the direction of the edges is important. We then talked about another extension where we could label each edge as either strong or weak. Now, the idea here is that if we consider, say, a social network, we may have strong edges that connect us to our close friends and family. We may have weak edges that connect us to coworkers or people we run across at a conference or event. We may know them, we may be willing to send an email to them, but we wouldn't consider them are close friends or are strong relationships. As we discussed this concept, we talked about the notion of strong triadic closure and how if two individuals are connected, so suppose we have three nodes, A, B, and C, and A and B both have a strong connection. The strong triadic closure property, if A were to satisfy this, it would mean that there must be some sort of connection here between B and C, either strong or weak. We talked about how it is sometimes weak connections that form local bridges. And we talked about that problem that Mark Granovetter proposed for his PhD thesis, where individuals claimed to find new employment opportunities more regularly through acquaintances rather than through close friends and family. And it's the key idea there was that often your acquaintances are ones with whom you form a weak connection. And the strong triadic closure property tells us that it is only a weak connection that could possibly be a local bridge in the presence of strong triadic closure. So these are the types of graphs we've talked about so far. And today we're going to add one more extension. And now we are going to talk about what is called a weighted graph. Now here, a weighted graph, the difference will be that each edge will be assigned a floating point number. So Python spells this just float. And this will tell us the give us a quantitative measure for exactly how strong a tie is or an edge is. So before we just had a binary classification that an edge could either be strong or weak. And now we're going to let this vary. An edge that has strength 0.5 is not as strong as an edge that has weight 0.8 or 1.0. And so we'll be able to talk about quantitative features of the network and its edges. We will not limit ourselves to strictly positive numbers. We'll say that any real number can work. And we might have the interpretation that a positive edge would mean some sort of friendly relationship, and a negative edge would be some sort of animosity. And here's this comment about kind of this qualitative scale of edge strength. An edge with weight +2 indicates a better or stronger friendship than an edge with strength of 0.2. Recall from our discussion of unweighted graphs that we can represent the nodes and edges of our graph using a special matrix called an adjacency matrix. In the unweighted case, this matrix was filled entirely with zeros and ones. Each row represented one node, and each column represented a different node. If we had a 0 in row I, column J, that would indicate that there is no edge between nodes I and J. On the other hand, if there was a 1 in row I, column J, that would mean that there is indeed an edge between node I and node J. Let's remember what this looks like. So here we have a graph that has 4 nodes labeled here 0, 1, 2, 3. And you'll see here that each node in this particular graph is connected to each other node. This is what's known as a complete graph. And we constructed it up here with that complete graph. Then we asked network X, once we had this graph G1, to convert it to a NumPy array for us. And This convert matrix to NumPy array routine will give us back the adjacency matrix for our graph. Here we see that, let's take the first row, for example. We have, this would represent node 0 in our graph. We have a 0 in the column 1 because we don't consider nodes that are connected to themselves. So that's why we have a 0 here. But we have a 1 in each of these other columns. This one in particular uh, will map into this edge right here between node 0 and node 1. And then we have the 1 in row 0, column 2, which represents this edge. And finally, we have row 0, column 3, which represents this edge. And so this is how our adjacency matrix, it could be visualized as a network. So we can extend the idea of an adjacency matrix to include weighted edges. Let's put a little story here. Suppose that nodes A, B, and C are friends, but A and C are really best friends. And also suppose that all of nodes A, B, and C consider D to be their enemy. Now, we might represent this scenario using a weighted graph as follows. The friend relationships AB and BC might be given a weight of 1. The best friend relationship between A and C might have a weight of 2. And the enemy relationships between D and any of the other nodes could have a weight of -1. Now, if we were to say that A is the first row, B is the second, C is the third, and D is the fourth, this would be the associated adjacency matrix. We have here the connection between A and B, between A and C, and then between A and D. Then we have the BA edge. Notice that this is symmetric because we're considering an undirected but weighted graph here, where any connection between A, B is the same as the connection BA. So here, BA has a strength of 1, BC has a strength of 1, and BD is -1. We can, once we have this array or weighted adjacency matrix, we can actually pass this directly to network X to construct a weighted graph. Here we'll call it G2. And I'm going to have a little helper function that will help us draw our weighted graph as well as label each of the edges with their weight. And so here we have that same structure we saw before with nodes 0, 1, 2, and 3. But now, because our adjacency matrix contain weights, we are going to annotate each edge with the weight of that relation. Notice that the node labeled 3 here only has negative edges. There's a -1 to 0, there's a -1 over to node 1, and finally there's a -1 over to node 2. This 3 represents D from our story. We then have node 0, which represents A, and we'll see here that there's this best friend relationship with a weight of 2 on node 2, which represents C. And finally, in the middle, we have node B. We'll use this helper routine to draw and label edges for weighted graphs throughout the notebook today. So one common question or type of problem that comes up when you are working with weighted graphs is known as the shortest path problem. We already talked about shortest paths for networks, and before, when we had unweighted graphs, the shortest path was the path that contained the minimum number of edges. Another way to say this would be the shortest path is the path between nodes 1 and 2 containing the least number of edges. Now, when we have a weighted graph, things actually get a little more interesting. Instead of having every edge with equal weight, you might just call it 1 for simplicity, we'll now have edges that may be more or less expensive to travel. Consider a network of highways in your local state or city. If you wanted to travel from one edge of the state to another, there are likely to be many possible routes or paths across various highways that would get you from one point to your destination. Now, suppose that we represented this using an unweighted graph. And anytime there was an exit or off ramp from a highway to a particular city, we included that as a node. So in our example, the edges are the actual physical streets or highways, and the nodes are each of the on and off ramps. Now, if we were to represent this physical map of highways using an unweighted graph, and we wanted to consider the shortest path between A and B, it might be that we end up taking a fairly long time to travel. So let's put a little example here. Suppose we have this is node A, our destination, or our origin, and then node B here is our destination. And suppose that we have edges that connect us in all of these places. If we were to try to find the shortest path through this unweighted graph, when we know we have to traverse this, and then this is 1, 2, 3, 4. The shortest path might be 4 edges. Consider, though, that we have a weighted graph where the weights are actually going to be driving times or travel time in minutes to get from one node to the next along a particular highway. Suppose that this node was 10 minutes, 5, 5, 2, 3, 5, and 20. If we take our shortest path in terms of the number of edges, the total travel time would be 20 plus 5 plus 5 plus 10 for a total of 40 minutes to drive from A to B. If, however, we consider the shortest path in terms of what is the lowest sum we can obtain traversing nodes between A and B or traversing edges, we would likely take a different path. In this case, the shortest time to travel would actually be this path in blue. And we'll draw it out and then we'll add up the number. So here for this blue path, it would be 10 minutes, 5 minutes, 5 minutes, 2, 3, 5. So here we have a total of 10, 27 minutes. So even though this ended up being 1, 2, 3, 4, 5, 6 edges instead of 4, it ended up being a shorter path because this little section here, 2, 3, 5, had a smaller total weight than this one edge of 20. So you can see how when we think about paths or the cost to move from one node to another through a graph, allowing the weights to vary for each edge results in a somewhat more interesting problem than if all the weights were simply 1. So what we'll do is we will give some notation here. We'll let WAB represent the weight for the edge connecting nodes A and B. If A and B are not connected, if there is no edge between these nodes, then the W is by default 0. Or you might, depending on your application, you might consider the weight to be infinite, meaning it's not possible to traverse that weight or that edge. We will then define the shortest path for a weighted graph between nodes n1 and n2 as the path that minimizes the sum of all weights for each edge that was traversed along the path. Similar to what we did up here in our example. So that's the problem we want to be thinking about. And we'll talk through an example and try to develop some intuitions. And then we'll learn a few algorithms or a few pieces of algorithms that will allow us to compute this shortest path for an arbitrary network. We'll now consider another example graph that will help us study this shortest path algorithm. I have stored in a data file called shortpathproblem.gml the structure of a graph that we'll be working with. We can ask Network X to read this in, and we'll store the result as the graph named G3. Now, to help us do some of our visualization here, we will make a dictionary that maps from the source destination tuple of an edge to the weight of that edge. And then we will also figure out where the position might be. This actually contains data on the position. So when we stored it in this GML format, we could remember to recall how the graph should be positioned when we visualize them. So then what we'll do is we will call the draw network X edge labels routine, as well as the draw routine. And this ends up giving us the following graph. We have here a collection of 7 nodes. And amongst these 7 nodes, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, looks like about 10 edges. And our goal, notice that this is both a weighted graph because each edge has a weight associated with it, and it's also a directed graph because each edge has an arrow. So this is called a weighted directed graph. And notice that the arrows all go out from A, meaning A is kind of the source node for our graph, and they all flow into G. So what we'll be considering is how we can traverse uh, from A to G in the shortest possible way. Stated here, our objective is to travel from node A to node G at minimum cost. Now, if we ignore the weights, we can see here that we can go straight down AD and then DG to only traverse 2 edges, and that would be the lowest or smallest number of edges we need to traverse. However, if we take into account the weight for each edge, we'll see that edge AD has a weight of 3, and edge DG has a weight of 8, and the total cost of that path, ADG, would be 11. Now, there are actually 2 other paths that have a lower total cost. One of them is ACFG, and the other is ADFG. And if we added up the cost of each of the 3 edges across and along these paths, we would get that they have a total weight of 8. Let's go ahead and take a look at what that would be. So we said that one of the paths was ACFG. So if we go down this path, we'll just kind of keep track of the total weight as we go. We have a weight of 5, now it's at 7, and finally it's at 8. The other shortest path in terms of cost was a 3 to get to D, and then 7 to get to F, and finally 8 to get to G. So either of these paths where we go kind of around the outside, or if we were to go down to D and then F and then G, either of these paths, even though there are 3 edges, the total weight is only 8. And these are the shortest paths in terms of weight. Now, we were able to kind of visually reason about and identify a shortest path for this graph because it was relatively small. There were only 7 nodes and 10 edges. And because of this, we were able to kind of reason through each possible path and what the total cost might be. If we were given a much larger graph, suppose we consider the graph of Twitter or of Facebook, or maybe the graph of all highways in the United States, it would be very difficult to try and find shortest paths between a pair of nodes on a graph of that size just by hand. In order to find shortest paths in larger graphs, we really need the help of a computer, which means we need to understand and implement an algorithm. That's what we'll be working on next. So let j of v, a function, be the minimum cost to go function from the node v to the node g. We'll talk in just a moment about more details what that is. Suppose also, after defining j in this way, that we know the value j of v for each node v. And below, what we'll do is we'll add this j of v value in red next to each node. So note here that j of node g is by definition 0, because what j is representing is the minimum cost to go from any node v until you get to node g. So if we say that we're considering v equal g here, the minimum cost to get to g when we start there is just to stay there and have 0 cost. Then we'll say that j of f, what is the least cost or the minimum cost possible to go from f to g? Well, this would be to go straight along the path fg, and this has a weight of 1. Let's consider j of d. Now, there are 2 possible paths that would get us to g. Either we can take the direct route, dg, which has a cost of 8, or we can take the route dfg, which would have a total cost of 5. Because this cost going dfg is smaller than the cost of going dg directly, we say that the value j of d is equal to 5. It's equal to the total cost of going first to f and then to g. If we consider the cost starting, say, at node b, there's a couple possible routes. One would be to go DEG for a total cost of 10. Another would be DBG for a cost of 17, or BDFG for a total cost of 14. Now that we have these 3 options, we consider which one has the smallest total cost. In this case, it would be BEG for a total cost of 10. And we can consider the other nodes here, but hopefully that illustrates the concept of what J represents as this minimum cost to go. So with J, V in hand, we can propose an algorithm that will help us find the cost minimizing path that goes from A to G. And here's how the algorithm would unfold. First, we will initialize the algorithm by setting lowercase v equal to A. And v will represent the node that we are currently at. And so because we want to start at A, we'll start off by setting v equal A. Then, from node v, we're going to move to any node that solves the following objective. We want to minimize over the choice of possible nodes n in what's called the neighborhood of v. So this notation f of v is all nodes V or all nodes N that are reachable from node V. So for example, if we consider that we are at V equal A, then F sub V is equal to the set C, D, B. Because these are the three nodes that have an edge where it can traverse from A to any of those nodes. So this idea of what is reachable from a node is called a neighborhood, and we give it notation F sub V. So it would be F sub A. So what we want to do is we minimize over any possible node in the neighborhood of V that minimizes the weight of traversing V to N plus the total cost to go J of the destination N. So what we're really doing is we're saying, okay, given that we know this function J, in order to minimize the cost of being at node V, of starting at V, we first have to take a step along one of our edges, and we have to consider that cost. And then, because we want to end up at G and not necessarily N, we have to add in the total cost that we'll still have once we arrive at node N. So this is really representing, if we've solved this properly, this will really represent J of V, should equal that. In the end, once we've optimized everything, that's what J of V will end up being. So once we've identified which node N in the neighborhood of V minimizes this expression, we will say that we're taking that edge, or we're traversing that edge. And the way we do that in the algorithm is we just update little v to now be N. And because remember, little v represents where are we currently in our graph. And then what we'll do is we'll just repeat these steps. So we'll kind of start back up here at step 2. Now that we have a new node, we've just updated which node V we're starting at. We then consider this objective function one more time, pick a new edge to traverse, and we keep repeating these 2 steps until finally we end up going to a node V equal to G, which is our ultimate destination. So let's implement that algorithm we just walked through. Below, what I've done for you is 2 things. First, I have defined a dictionary J3 that represents that function J of V for our graph G3. If you remember when we were displaying this graph here, we called it G3. And so to be consistent, I labeled this cost to go dictionary, I labeled it J3 so it matches up with G3. And I've also defined for you kind of the structure or scaffold for a function traverse graph that looks like this. So here we have a few arguments. We have G, which is a network X directed graph. So let's go ahead and look at what that is. If we do type of G3, we see here that it is indeed one of these directed graphs. So we take as an input the graph, we take as a second input this J function. We then are allowed to specify the start node and the end node. And what I've set up for you, I've set up a lot of the code, but you'll notice here I have a few to-do steps. So there's 1, 2, 3, 4 to-dos. And what we want you to do is replace the code here so that we can actually initialize V properly. So here I've hard-coded V is equal to A, But you've got to remember that we're writing this function with the intent that somebody can pick their starting node via this argument. So let's look at what I've set up for you and what we're asking you to do. So first, I set up a list called path that contains for now only our starting node. We're going to add to this each node that we visit so we know what path we're going to take through our graph. We then have a total cost of 0, and we have W here is that adjacency matrix for our weighted graph G. And here I have a little typo. I should write this as just G instead of G3 because we have to take into account this argument. So then what we'll do is we're going to ask you to pick a starting condition properly. And then just so that we don't end up in an infinite loop, we're going to keep track of the number of iterations. Because we know that the number of iterations has to be less than the total number of nodes because any shortest path between two nodes at most will visit every other node in the graph. So we'll make sure that we don't iterate too many times. This could happen if there's an error or bug in our code down below. So this will prevent your computer from running infinitely until the end of time, trying to do incorrect steps solving the shortest path problem. Okay, so the condition that we're going to stop, though, is while v is not equal to the end node. So continue going until v is the terminal node that the user asked us for. We'll keep track of this iteration. We can ask G for the neighbors of v, and we'll call this f sub v. So this maps directly into the f sub v we had in our description of the algorithm above. In particular, it is a list containing node labels for every node connected to v, or reachable by v. We then have another to-do item for you. We're going to ask you to compute the cost for each of these nodes in the neighborhood of v. So you're going to have to use the weight matrix W, and you're also going to have to use J in order to get the total cost of moving from, say, V to N here in our notation. Then what we'll do is after you've given this cost array, I will compute for you the index of the minimizer and pull out the associated node. So I'll take care of figuring out which node we actually visit. And then you are responsible for updating the cost and also updating V according to what we said in the algorithm. So you have 4 to-dos, and then we've done the rest for you. And I'll go ahead and delete this code. You should do the same. And once you've written this code, you should be able to check to see if you got it right. So I have here a cell that will just evaluate the function. And this will let you see both the path and the cost so you understand what's coming out. And then here we have some tests. And if you've implemented this function correctly, when you run this cell, the output should be blank. There should be no output whatsoever. If there's any kind of bug or mistake in the code, the output would have an error. It would be probably in red, and it would tell you that there's an assertion error or a problem somewhere. So go ahead, pause this video, take a few minutes, and implement this traverse graph algorithm, and go ahead and check your work down here. Make sure you did it correctly. All right. Hopefully you were successful in your implementation of that traverse graph function. And now we have one more hiccup to consider. So that function, if you remember, took as arguments both the directed graph G and the cost to go function J. in addition to starting and ending nodes. Now, we took as an assumption that we had j ready to go, but often when we're given a graph, we will not also be given this cost to go function j. So the question is, how can we actually compute the cost to go function given just our graph, and then maybe starting and ending node? So I kind of hinted at it above when we talked about the algorithm, but if you stare really hard and for long enough at the following equation, you can convince yourself that the following identity must hold for the true cost to go function j. So we say that j of v for any node v is equal to the minimum over all nodes n in the neighborhood of v of the weight of the edge from v to n plus the cost to go function at n. Another way to think of this is that if we want to compute this cost to go function j, we can break it into two subproblems. First is the immediate cost of taking an edge or moving along an edge from v to n plus the future cost once we've already arrived at n. And if we minimize both this immediate cost and kind of adding in the future cost, that will give us the minimum cost starting at v. I'll say that one more time in slightly different words. What j represents, j of v, is the minimum cost to go starting at node v. This must be equal to the minimum of the immediate cost for the very next edge we traverse, plus the cost to go from the destination of that edge. Now notice that this function here, we're kind of defining j, something that we just argued was unknown, in terms of itself. This is called a recursive function, or the recursive formulation of the cost to go. Now, when we think about this, should be very reminiscent if you've studied some intermediate to advanced macroeconomics. You've likely run across recursive formulations like this. Where often, instead of calling it the cost to go function, we may have called it the value function. And when we have a recursive formulation of an unknown function like this, it really stems from brilliant economist or mathematician named Richard Bellman. And we call this type of equation a Bellman equation. Now, what J really is it's not necessarily a definition of J, but rather a restriction that J must satisfy. Think about it this way. If we're given some candidate function, maybe we're going to call it J hat, is like a candidate cost to go function. In order to verify that it is indeed the minimum cost to go from each node, we would simply need to check that this condition holds. Uh, we check that j hat holds for every node v, and if it does, then we can say that j hat is indeed the minimum cost to go function because it satisfies the restriction imposed by the Bellman equation. What we will do using this Bellman equation is we'll actually use this restriction to be able to compute j given only a graph and an intended destination node. So here what we'll do is we'll kind of present the classical or standard algorithm that's often used for solving recursive functions like this. This is going to be an iterative method, meaning that we'll start with some guess, some candidate j hat, And we'll actually use the restriction to update our guess. And as we apply that Bellman equation to our guess over and over across many iterations, it actually turns out that we will end up with a final guess for the cost to go function that satisfies the Bellman equation at every node, and thus is the true cost to go function. Here's how it works. Let the lowercase I represent the iteration we are currently on, and j sub I is a function of our nodes that is the current guess for the cost to go function jv. So this is just a bit of notation, and then the algorithm proceeds as follows. We'll start off saying I is equal to 0, and we'll just propose an initial guess, j sub I or j sub 0 equals 0 for every node. Now we know that this is false, but it's okay. It's okay to start with a wrong guess. We have to start somewhere, and I don't want to call it magic, but the brilliance of this algorithm that Bellman gave us is that given any guess, we can actually follow these steps 2 and 3, and we'll eventually converge on the true answer, J of B. So the way we do this is if we start an iteration with a current guess, J sub I, we'll set Ji plus 1 at each node V equal to the minimum over all nodes n in the neighborhood of V of the weight of that edge from V to n plus our current guess, Ji, of the cost to go from the destination n. So if we consider what might happen on the very first iteration, well, J sub I will be 0. So this term basically drops out. And we'll start off by considering taking the edge of all the possible choices that just has the lowest weight. And that's kind of how we kick things off or get things started. Now note that the weight that we'll have, the minimum weight that we've just computed, and set J1 equal to that, will make J1 different from J0 at all nodes except our destination. So now we've updated or changed our guess for J. And the final step in the algorithm, or within this loop, I guess, is to check if Ji and Ji plus 1 are equal for every node. If they're not, let's kind of bump up our counter for which iteration we're on, apply this same operation again, and now this time, instead of all zeros, we're going to have an updated kind of notion or measure of what the cost to go is from the destination end. This will then mix with the single edge weight to give us another updated value for J. We'll check if those are equal. If they're not, we'll continue. And by repeating these steps over and over, we will eventually, under some fairly mild regularity conditions that for our purposes, we assume always hold. Applying these steps 2 and 3 iteratively will always lead us to the optimal function J. Now, we're not going to prove it, but hopefully you can take my word that for the cases we will consider, this algorithm works. They satisfy whatever conditions are necessary for the proof. So let's see how we can implement this. We want to compute this function J, where the arguments of this compute J function include the directed graph G as well as the destination node. And we've implemented the whole function here. There's not an exercise. And so what we'll do is we'll just kind of walk you through our code. So here we go. First, we'll start by keeping track of how many nodes we have in the graph. And then what we'll do, because these nodes might have different labels, for example, in our graph, they have letters A, B, C, D. What we'll do is we will make a dictionary that maps from the node name, here A, B, C, or D, into an integer, which would be 0, 1, 2, 3, 4. We'll need this a little bit later on. We'll need to be able to go from a node to an index because these numbers are going to be helpful for accessing elements of a list or an array, and that's what we really need. We're going to also have the inverse mapping where suppose we want to go and say, well, which node corresponds to index 3? Well, that would be node D if we were just thinking alphabetically. We're just going to kind of invert this dictionary. So we can go both from a node to an index or from an index to a node. Now, we said that step 1 of the algorithm was to set I equal to 0 and ji equal to 0 for every node. Because we have n nodes, we'll represent ji using a length n array. And just like we said, we'll initialize that to n zeros. Then what we'll do is we will take the W matrix. We'll ask network X to give us that weighted adjacency matrix from the given graph. We'll say we're not done yet, and our loop will be while we're not done, we'll go ahead and add 1 to I, and then we'll do a loop. So it says for each V in G dot nodes, what we'll first do is figure out, okay, which element of our cost to go function J are we considering? Or which row of W should we think about? And to do that, we go from the node label to the index using the dictionary we constructed above. If V is where we want to end up, we kind of have to impose this boundary condition that the cost to go function at this node, at node V, is equal to 0. So we'll impose that here, and then we'll do continue. And what this does is it stops the for loop at this point and goes back up to the top. So we skip these lines of code. So anytime we visit the destination node, we just impose the condition that the cost to go is 0, and we don't need to do any more. Then what we'll do is we will construct we'll look at the neighbors or the neighborhood of V. We'll compute the J half. So if you remember, what we're trying to compute here is we're saying that J I plus 1 at B is the minimum over N in FB of WVN plus JI of N. So what we have here is this cost right here. Here we have the Wij plus a Jij. This is the right-hand side. So we've computed for every n, we now have this expression here. And then what we'll do is we just need to apply this min operator right here. And that's what we do in this line. So these j's, it's a little confusing. I probably should have picked a different letter. But what these are column labels in our weight matrix. So we have a row label I, and then we have a column label J. So what we're doing is for each J, for each column label, we're going to say what is the weight from row I, column J, plus our current guess for the cost to go function once we arrive at node J. It's a little confusing. This lowercase j doesn't really have anything to do with the big J. It's just going to represent which node we are considering visiting, which element of this neighborhood are we going to traverse. So once we've considered this loop here for all of our nodes, we will then check if the next j, so this is ji plus 1, is equal to ji. And if it is, we will say that done is now true, which will cause the loop to exit. And then we'll just update and we'll bring over all of the next j's, we'll put them into ji, so that when we begin the next iteration, have our updated version, or updated guess for the cost to go function. We will continue kind of looping through all of our nodes, updating the cost to go until this key condition here on line 26 is satisfied. Once it is, we'll stop and we will return the cost to go function we ended up with. So this is our implementation of that algorithm above. So if we then ask for the j function starting at, for graph G3, ending the cost to go in order to reach node G, what we end up with should look very familiar. It should look just like our J3 did in terms of the numbers. So here we said that A, which we said was index 0, had a cost of 8, 8, and then 10, 10, 3, 3, 5, 5, 4, 4, 1, 1, 0, 0. So we've kind of shown or evaluated an example here that lets us believe that we've implemented this algorithm correct. We started with a guess of zeros. We ended up with the known solution that we could compute by hand. And so we feel pretty good that our function is correct. So the last step here that we have for you is to combine the compute j and traverse graph functions that we've written up above in order to be able to find the shortest path given an arbitrary directed graph and a starting and ending node. We want you to be able to give us the shortest path. The outputs here should be the same as the outputs from the traverse graph function up above. And what all we need to do is we need to call the compute j function. We just need to pass it the right subset of our arguments. Once we have that, we then call and return the value from the traverse graph function. So what we'll ask is that you take a few minutes, you implement this routine here, you combine our two smaller functions up above, and then you can test your work down below using this cell. Again, if you've implemented the code correctly, when you evaluate both of these cells, down here you should see no output. So what you're hoping to see is nothing. If you do see some glaring red error messages, that means that you should probably take a closer look. Yeah. So we will encourage you to take a moment and pause, and then we'll come back for just a minute to wrap up our discussion of weighted graph. So go ahead, pause the video, work on this exercise, and once you've solved it, you can resume the video. Okay. Hopefully you were successful in implementing that shortest path routine. And so now we'll kind of bring it back together for our final summary or takeaway. So today we studied an extension to our model of graphs that allowed us to attach a weight to each edge in the graph. And we call this type of graph, where each edge has a different weight or numerical value, we call it a weighted graph. And the applications of weighted graphs are very broad. So some examples that come immediately to mind are we may use a weighted graph to analyze traffic flows. Now, these could be traffic flows on physical roads or bridges. Maybe it's flows of electricity across power lines. Maybe it is flows of data across network lines at some cloud facility or server farm, but trying to think about how maybe the wait for these traffic flows for an edge might be the time required to move from A to B, or it might be the capacity of that particular edge. If we're thinking about power lines, maybe we need to represent the capacity of a particular transmission line using a weighted edge. There are also other examples. If we want to think about resource planning, maybe we're doing deliveries. We're Amazon, and we're trying to deliver a huge quantity of goods to various locations across the country, and we can only have a finite amount of goods on each truck. How might we consider optimally dispatching trucks across the network of highways in the United States to make sure everybody gets their goods? Another one might be analyzing supply chain issues. The edge could represent either the actual flow of goods from one uh, firm to another, or it might represent the cost of one firm selling to another. Another example could be international trade. Suppose each node is a country and each edge represents the unit cost of exporting or moving one good from one country to another. Now, depending on the tariffs structure between different trade partners, it might be optimal instead of, say, the United States buying directly from another country, we'll call it country X. Suppose the tariffs are high between the United States and country X, but the tariffs are low between both the United States and country B and country B and country X. In this case, maybe it is more cost effective for X to sell directly to B and then B to sell to the United States. And this we avoid the high tariff path from X to the United States directly. So there are many, many more examples of weighted graphs. And it's really a key theoretical concept that we wanted you to understand. The other main takeaway from today has to do with our programming. So, what we did as we studied the shortest path problem was we ended up with a function called shortest path that could be handed a directed graph, a source node, and a destination node. And it was supposed to give us the path and the associated cost of going from node 1 to node 2 in that graph. Now, if you implemented that function like I did, it only had 2 lines of code to do that entire kind of fairly complex operation. The way that we were able to have the more complex kind of overall algorithm, shortest path, only be 2 lines of code was that we just implemented 2 smaller routines called traverse graph and compute J. So we ended up with a total of 3 functions. And for each of these functions, we were able to write some tests that verified the correctness of our code. For give an example, this type of test where we provide example inputs and check the outputs to something we've previously computed or known is called a unit test. We're testing the functionality of a single unit of our program or a single function in our code. Now, each of the 3 functions, again, we had tests for them. And this is actually a very good habit that we strongly encourage you to continue using as you further your programming skills. And the big picture principle is that often we're going to have some overarching task that is fairly complicated, fairly difficult. And it becomes much easier to write correct code if we break a big problem into several smaller problems, where what we can do is write a single function to tackle one subproblem that's kind of well defined and self contained. And then we can implement that routine all by itself and test it and make sure that that part of our program is working. We can then move to the next subproblem, write the implementation, test it, make sure it's working, and so on for all of our subproblems. And then the overall routine will just be some composition of these smaller building blocks we've been creating and testing over time. Now, there's one more line here. It's not showing up, so I'm just going to exit slide mode real quick. Um, what we'll say and point out here is that not all practitioners actually do this. I'm going to make this a little bigger so we can see it. So, what we often have seen in the wild as we've worked with different teams is they might have one overall goal. They want to fit some machine learning model or solve some economic problem. And what we've often seen is that their code ends up being one big long list of instructions, either in a Jupyter notebook, where you're supposed to hopefully be able to start at the top, execute cells sequentially, and end up with a result, or as one big long script or file where you just have the instructions laid out one after another, or something fairly large and complicated. This is extremely hard to verify correctness if we're trying to only consider the full program in its entirety. It's almost impossible to prove that it's correct. But if we have each piece of core functionality kind of in its own place, and we can test that little piece of functionality in isolation, then it becomes much more manageable to verify the correctness of the program as a whole. So think about it. If we have 1,000 lines of code, it's pretty hard to verify that this single routine of 1,000 lines, that each line is doing exactly what it should. Suppose we break that into maybe 50 little functions, each of 20 lines of code. It's pretty easy compared to 1,000 lines to verify that a 20-line piece of code is doing something correct. We can, with our limited mental capacity, kind of keep in mind the whole context surrounding that 20 lines of code in a way that's really not very feasible to do for 1,000 lines. So even though we'll have 50 kind of checks to do, each of them is much more manageable and actually possible compared to the daunting task of verifying the entire program. So we strongly encourage you and frankly expect that as you continue forward in writing code, you can follow these good practices. Take a big problem, make it into smaller ones, test each piece by itself, and we now expect this of you. You've been taught, you have the skills, now go forth and apply that. So this is the end of our discussion here on weighted graph.